So when deciding the appropriate parking orbit for the depot, you had to take the approach that mass is money. Each extra kilogram that we can deliver to geostationary orbit represents more mass of propellant that can be sold. So this decision was made in tandem with the launch vehicle. This comes with a trade-off. The lower the orbit, the more mass we can get on the depot, but the more mass is going to be expended by the propellant transporter getting to and from geostationary orbit. And this is a table that shows that given that the orbit where we can get the most amount of refuels per depot is geostationary orbit at 0 degrees inclination, which is exactly where our customer base is. And this table assumes a purely hydrazine depot, but the principle still holds for a dual xenon and hydrazine depot because the propellant transporter is relying on hydrazine to do its maneuvers. So how do we know the exact orbit is geostationary orbit? Because as was brought up in PDR, if we were to lower this parking orbit to a sub-geo, we could get more mass there, and we could rely on automatic phasing. So yes, we could get more mass to a sub-geostationary orbit, but because the propellant transporter has a higher inert mass fraction, a lower specific impulse, and has to go to and from geostationary orbit, you can't get as much propellant to geostationary orbit, even though you can to the parking orbit. And you would need an infeasibly high specific impulse, close to 4,000, for an impulsive engine for this to not be the case. As for automatic phasing, when you're in geostationary orbit and you want to phase to a customer, how much propellant you use is dependent on the demand level. The lower the demand level, the longer you can take to phase there, meaning you're going to use less propellant. So for any given demand level, you can say, okay, well, how much propellant does that use? And you can pick out an orbital radius or an average you kick from that radius to geostationary orbit uses the same amount of propellant. But unfortunately, for this radius, the synodic period between that and geostationary orbit is too long. It can't support a given demand level. So this begs the question, does there exist some optimal split between automatic phasing and impulse phasing? And the answer is no. Phasing purely in geostationary orbit represents the way to save the most amount of fuel. And this holds true for elliptical orbits as well. So essentially, we want our apogee and perigee to be both at geostationary orbit. So now Patrick's going to go ahead and talk about longitudinal placement.